Hello, everyone. Good morning from Brasilia. It is a great pleasure to have you all here in our session, plenary session today. It is a great honor to be chairing this mechanics plenary talk of our 14th summer workshop in mathematics, the 14th edition of this very nice event that we organize here at the University of Brasilia. So I will just go briefly on how things will work here. I will briefly introduce our speaker today. He will speak for about 50 minutes or so, and then we will have a few minutes for questions that you might want to ask. So the way you should interact with us is via the comments, via the chat window on the left of your, on the right of your video, of YouTube video, and I will read your questions to our speaker. Okay. So I think that's it. It is a great pleasure to introduce our speaker today, Chris Johnson from the University of Manchester. Chris, welcome to the University of Brasilia. It is a great pleasure to have you here. So Chris did his undergraduate degree in mathematics at the University of Cambridge. He graduated in 2007, and then he went on to do a PhD under Nico Gray at the University of Manchester. He graduated in 2011, and then he went to do postdocs at the University of Bristol under Andrew Hogg. And since 2015, he is a lecturer at the University of Manchester, now holding the position of senior lecturer. So Chris has been working with granular problems, granular material problems, and also with flows of ash transports from volcano eruptions. So this is, we've just heard about the Tonga volcano, right? So Chris is probably looking at that as well. But today, Chris is going to talk to us about very fast debris flows that happen in nature and the mathematical models that he's been using to deal with them. Chris, it is a great honor to have you here. Thank you so much for being with us. You can start your presentation. Thank you.
Thank you, Yuri, and it's a great honor to be here. So as Yuri said, I'm going to be talking today about debris flows and avalanches, these rapid granular flows that occur in nature. And we've seen a couple of very prominent examples in Brazil just over the past few weeks, one which I was discussing this with Yuri before, one of which destroyed a very old colonial house, and the other which unfortunately killed some people in boats. But it just goes to illustrate how widespread these problems are. And I'm going to be talking to you a little bit about how we can use mathematics to do some modeling and prediction of these things, and also some lab experiments. So while I am in a maths department, I do lots of other things that I think would be considered engineering or physics in some countries in the world. I do those from a maths department. So I'd like to present some work that I've done with my colleague Nico Gray in Manchester, along with a Brazilian PhD student, Chico Rocha, who graduated a couple of years ago and is now doing a postdoc in Marseille, and a couple of other postdocs with us in Manchester, Andrew Edwards and Sylvain Virelet. So to start, I just thought I'd show you a video of what a debris flow actually is, and this is a debris flow from 2002, and I'll just let the video play so that you can hear what's going on. In fact, it's quite noisy where I am. I'm not sure if you can hear it, so I'm going to take my headphones off a bit so that I am not deafened by the sound of this. So what you can see is that we've got a riverbed here in Semeru, which is in Indonesia, and it's covered with a mixture of rocks of all different sizes and mud and water. And then what we've got flowing down, you can see in the distance coming towards us, is a mixture of a very similar mix of rocks and water and debris and mud. And this has been eroded from further upstream and is now traveling down. And we'll see as the flow front passes us that really there's an awful lot of rocks and things in there. So it looks like a fluid, but actually the majority of this, in particular, the majority of the weight of it and the majority of its volume is composed of solid particles of rock ranging all the way from sort of meter-sized boulders that you could see there all the way to down to clay down at the kind of 10 micron diameter, all of which in this case is suspended within a water. I thought I'd show a much less dramatic, much more peaceful avalanche, just to show that the water is not a key constituent of these things. It does change the behaviour of such flows quite dramatically, but it's not essential. And what we can see here is an avalanche on the side of a sand dune in the Colorado Dunes National Park in the United States. And this just starts with a few seconds of black, but I think you can then see what we've got here is just a layer of maybe 5 or 10 centimeters deep on the top of this sand dune is breaking off and is rolling down towards the person filming. And this obviously isn't very dramatic. It's not a very powerful landslide. This is just a brief video. I'll play it again because the person is just happily standing there and it's washing around past them. So these are just 2 examples of a really very diverse array of flows that we get in nature, where the key constituent is that we've got some kind of granular material, some rocks, some particles of some size, and they're flowing downhill. And we obviously get the same things when we have snow avalanches or rock falls or other sort of similar processes. And so what I thought I'd do is describe first, just go back to as simple as possible terms. What do we know about flows of things going down hills? Really, in a single sentence, that's what's happening. Gravity is pulling this material down the slope. So describe a little bit about the mechanics of that, starting from the first principles. Talk a little bit about how granular flows in particular differ from the fluid flows, which you might be more used to seeing, and then give some examples of some laboratory experiments which mimic the kind of features that we can see in nature, and how we can then describe those laboratory experiments and thus the natural phenomena using mathematical modelling. So, as I say, I thought I'd start from the very beginning and just look at the very basics of flows going down slopes. I thought, so let's think about what the simplest example is. Well, let's just consider what we have if we have an open channel flow of a Newtonian fluid, viscous fluid, flowing down an incline. And as many of you may know, Newtonian fluids have a shear stress that is proportional to the shear rate and is with a constant of proportionality, which is constant. That's what makes them a Newtonian fluid, and that's the viscosity. And important, this shear stress is independent of pressure for a Newtonian fluid. And so if we've got some flow like this going over down some inclined slope inclined at angle zeta, we have some flow of thickness h, some layer of viscous fluid, and gravity is pulling it down the slope. And so there's some kind of velocity of this flow moving down slope in this direction. And there's some velocity profile. And how can we work out the velocity profile? Well, we can solve the Navier-Stokes equations. And so what we end up with is a balance, as I said, between gravity pulling this material down slope and viscosity, which is resisting that motion. And so this is represented in this equation, which is just the Navier-Stokes equation simplified for this particular scenario. We've got rho g sine zeta, which is the component of gravity pulling the flow down slope, balanced by eta times d squared u by dz squared, which is the viscous stress term. And so this is just a second order boundary value problem. What are our 2 boundary conditions? At the bottom of the flow for fluid, we know that the velocity must be equal to the velocity of the boundary, so u is 0 at the bottom. And at the top of this, because it's an open channel flow, we have no shear stress, and so the gradient du dz is equal to 0. And so with this equation, these 2 boundary conditions, we can just solve to find that there's a quadratic a profile, a sort of parabolic profile, sometimes called half parabolic because we only see half of it towards the open channel surface. And so this is the velocity. Now, what I'm going to be interested in talking about mainly in this talk is about thin flows. The 2 flows that I showed you from nature are both very thin in the sense that, they were maybe one was a few centimeters thick, one was maybe a couple of meters thick, but they're thin compared to their length scales. Both those flows were many meters, or in the first case, many kilometers long. And so we'll be looking at ways of exploiting that by depth averaging the flow. And so at this point, I'm going to just introduce how we can depth average this quantity. If I take my velocity profile u and integrate this over the depth of the flow, and then divide by the depth of the flow. This just gives me my average velocity, which I'll call u bar. And then for this Newtonian fluid, that's just some parameter which depends on the slope angle and gravity and the viscosity times h squared. So for a Newtonian fluid, the average flow velocity is proportional to h squared, and that doesn't matter what the value of h is, it's always this h squared scaling. So that's the simple fluids case, which I think may be familiar to many of you. Let's now look and see how this differs with granular materials and the kind of effects that has. So granular materials, by definition, are made up of solid particles. And if you're thinking about solid particles going down a slope, the first thing that may come to mind is these kind of sliding block experiments, the kind of mechanics that you might have done at school, where you've got some normal reaction force, and then we say the friction between the solid block on the solid incline is some constant mu, the friction coefficient, times the normal reaction force. And this kind of stress, this kind of frictional stress, is different from the viscosity we saw in a fluid, because whereas fluid viscosity is independent of pressure, here the shear stress is linear in pressure. That is, effectively the shear stress being exerted at the bottom of this block is proportional to the pressure that's exerted at each point. And that's just the continuum way of expressing the fact that friction is proportional to the normal reaction force. And so how does this kind of solid frictional behavior determine how a granular material behaves, when a granular material is obviously more complicated than a single sliding block? It's instead lots of grains, lots of solid grains contacting and sliding and all rolling over one another. Well, it turns out that actually the frictional behavior is quite similar, but with the difference that the friction coefficient, instead of being a constant as it is if you've just got a block sliding down a slope, is now a weak function of something called the inertia number. And this is itself a function of the shear rate, du dz. So we get some shear rate dependence, the particle size d, the pressure p, and the grain density rho. And so we've got a slightly different way of working out how granular materials behave. But if we use this approximation, I should emphasize this is an approximation, but if we use this, let's see how far we can get. Well, we can do a very similar analysis, and I won't go through this in detail, but really we've got exactly the same setup, but now instead of looking at a Newtonian fluid, we're now looking at a granular flow down an incline. And all I've done is I've taken exactly the same parameters, but I've just replaced that Newtonian viscosity with this mu times p, which is the granular shear stress equation, and that's now being balanced against gravity. And so if we solve this, what we end up with is a differently shaped velocity profile. What we find here is that the depth average velocity is some function of the slope angle, which I'm not going to explain in detail. That's a little bit more complicated than it is in the fluid case, but it's multiplied by the thickness of the flow to the power 3/2. And so instead of squared for a Newtonian fluid, we get 3/2 for a granular fluid. And this emphasizes that granular materials are non-Newtonian fluids. And so if we take this rheology, which I've described, the so-called mu of I rheology, this predicts that the average flow velocity is proportional to h to the 3/2. But is it? Well, maybe. Let's look at some experimental data and see if that's actually the case. So what I'm showing here now is some experimental measurements that we've taken. Essentially, on the horizontal axis here, we've essentially got a non-dimensionalized velocity. This is u bar. I've divided it by a velocity scale, root hg cos zeta. But essentially, this is a non-dimensionalized velocity. And this is the thickness of the flow, and I've represented this in terms of grain diameters. And what we can see here is that if we take our experimental measurements, we can see that the Froude number, which is this non-dimensionalized velocity, scales as h. And because h comes into the definition of the Froude number, this is equivalent of what I said before, that the depth average velocity is proportional to h to the 3/2. So far, these data seem to be agreeing with the theory that we have seen that I showed in the previous slide. But let's take a look at one of these data points and actually have a look at what experiment was done to gain this data point, and let's see what really happens in that experiment, more so than just measuring the steady state velocity. So what I'm showing here is what's called a space-time plot. On the horizontal axis here, we have time in seconds. In the vertical axis, we have x, which is our downstream coordinate in centimeters. So up here at the top is the top of our experimental incline, and down here, 35 centimeters is close to the bottom of our experimental incline. And so what we can see at the start of this flow, we have a steady uniform flow of grains. We're feeding in grains onto this slope from a hopper at the top of the up here, and the grains are flowing down, and we can work out their velocity in part by looking at the gradient of this sort of slope we can see with time. These diagonal lines, which we can just about make out here, we can quantify those. In fact, we don't use quite this kind of plot to do that, and then use that to measure the surface velocity. But what happens when our hopper runs out of material? Eventually, we're going to run out of material at the top, and our flow is going to stop. And what we see, in fact, what's been known for some years now, is that not all of the granular material drains off our incline. Instead, we get left with a thin layer of grains which are stopped. And we can see the process by which that happens here. We've got our flow coming down like this, and then between these two dotted white lines, there's some kind of stopping wave where the material there is decelerating and coming to a stop. The stopped material looks like horizontal lines here because nothing is changing with time. And this deposit has some thickness. So it's not like a viscous fluid where if you leave it long enough, asymptotically, all of the material, all of the fluid drains off. Here we get left with some static layer of some thickness. And this is really key because a lot of the granular flow problems which we look at, and a lot of the ones we see in nature, have both flowing material and stopped material. So what we can do is measure what the thickness of the layer that is left behind by these avalanches is compared to the slope angle in degrees. And so what we can see is for low slope angles, sort of 22, 23 degrees, we get left with quite a thick layer of grains, here about 2 millimeters. And as the slope angle increases, that layer of grain that's left behind static on the slope, it gets thinner and thinner. And so if we go back to our plot of the velocity, the non-dimensional velocity of particles against the thickness, we've also got that at zero velocity, we're ending up with these particles at some thickness h stop. And what was observed again about 20 years ago or so is that what's a good idea is to rescale your vertical axis, your thickness of the flow, in terms of h stop. This is the thickness of the static layer. And the reason that's a good idea is because we can then take lots of different experiments at lots of different slope angles, and all of those data then collapse onto a single line. So I've added on lots of other crosses, which have all been collected at different slope angles. And so we've now got a description of what the non-dimensional velocity, the Froude number of the flow is, in terms of the thickness of the layer that then is left behind. And that scaling works for a whole different range of slope angles. But we can see that actually our data only goes down to some particular velocity or some value of the Froude number, which is about 0.2. And below there, we haven't got any data. So let's zoom in on that region. This is just the same plot. I've just zoomed in a bit, and think about what's happening in this very slow region. Well, what we know is that you can have static layers of thickness h stop, because that's the static layer that we see after our avalanche is finished. So there is, in a sense, there's another data point where this red cross is, where this red circle is, I should say, where we can have granular flows in that state of thickness and velocity. And in fact, we can see static granular layers over a much wider range of thicknesses. It turns out that, so this red line and the black data points are the same data. This is the thickness at which of the layer left behind by our granular flows. But it turns out that if we take one of these data points and we then increase the slope angle, so I'm moving to the right here, it turns out that that layer doesn't then fail and start flowing again until we reach a much greater angle. And we call that angle h start. We call the thickness at a given angle at which the layer fails, h start. And so what we end up with is being able to see, or we'd be able to sustain static layers on an incline, static layers of granular material on an incline over a range of thicknesses, all the way from 0 thickness all the way up to this this thickness h start. And again, these open circles are experimental data that we've used to measure that. And so what we end up with then is some more data points where all these crosses here are static layers. U is 0, so they're static, on the inclined plane, and those exist all the way up to this thickness h start. And so the question is, well, what's going on to link static material and flowing material? We've got this gap where we don't really have any data. We can't see any steady uniform flows, so we can't measure the steady uniform flow speed, but equally the material isn't stopped either. And in a series of 3 papers in 2019, the group in Manchester looked at this, looking at 3 different experiments to try and characterize the behavior of this regime. And what we found was that there was this sort of intermediate frictional regime where, in fact, steady uniform flows can exist but are unstable, and that's why they're never observed in experiments. But what we were able to do was characterize the form of this intermediate friction to a much greater degree of accuracy than had ever been done before. People sort of recognized that something like this might exist, but what we did was look at 3 separate experiments which were quite sensitive to the form of this this region and use that to deduce what it was. So I'm not going to go into detail about exactly how we did that. That's another hour's talk by itself. But instead here I'm going to show some of the consequences of that. So let's talk about what we can do. Once we know that you can get static layers up to some thickness and you can get flowing layers which obey this, the depth average velocity scales as the thickness to the power 3/2, we can formulate what's called a friction law to describe this experimental behavior that we've deduced in terms of the basal friction coefficient, which I'm calling mu b, and this is essentially the equivalent of that friction coefficient that's at the bottom of the sliding block, the simple mechanical block sliding down a plane. And what we see is that we have both static and dynamic friction coefficients, and in fact that's true just of a sliding block as well. You can have a static friction coefficient that's larger than a dynamic coefficient. But in this case, we also have an intermediate friction coefficient, and the dynamic and intermediate coefficients are dependent on both the thickness of the flow and its velocity. So there's a velocity dependence in there as well that you don't get with classical friction laws for solid objects. But by characterizing this, we end up with this sort of hysteretic sort of solution where we can have, if we look at between this thickness h star and h start, which is up here, we have a range of thicknesses over which there are solutions that I'm highlighting here where layers of that thickness can be static. And we have solutions over here where layers of that thickness can also be flowing. And so in a sense, there's some of you may recognize this kind of pattern as a hysteretic structure where we have 2 stable solutions, 2 limit points, one here and one here, and an unstable solution in between them. And we can switch between this flowing branch, which I'm highlighting, jumping to static layers, and then from the static layer jumping to flowing layers through transitions, hysteretic transitions between those 2 regimes. And I'll show how those kind of transitions explain some of the behavior where we have interaction between static and moving granular materials. So I said earlier that the granular flows that we're interested in are typically ones that are very shallow. And so what we tend to use is depth integrated modeling. So instead of describing the full three-dimensional velocity of all the grains at every point in space and time, we instead look at the thickness of the granular flow as a function of x and y, which are kind of the two spatial coordinates along our plane. And we look at its depth integrated velocity, u bar, in the downslope direction and v bar in the cross slope direction. And so what we're looking for is equations which tell us the evolution of h, u bar, and v bar. And the equations which do this, as is so common in mechanics, are mass conservation and momentum conservation. The mass conservation just tells us that the thickness of the flow varies according to the divergence of the flux, which is going into that point. So if there's lots of material granular flows coming towards a single point, the thickness at that point will increase to accommodate that mass. And the momentum conservation equation, this is the tricky part. There are some well-established parts of this equation. So inertial terms, thickness gradients, these are saying that if you've got a big pile of granular material, then gravity tends to reduce those gradients and that pile tends to slump, as you're used to seeing. If you turn a bucket of sand upside down, you know it slumps because of these thickness gradients. If our situation is on an incline, then gravity is pulling our material down slope. And then we've got two components coming from the rheology. We've got tau xz, which I'm calling, these are the shear stress components due to friction with the base of between the granular material and the base of the flow. And then we've also got some higher order stress components. This D is the sort of strain rate tensor based on the depth average strain. And this is a quantity which is not usually included in these kind of depth average models. It's usually included only in higher order models, but as we'll show, it's essential for some of the problems that we need to look at. And so these kinds of equations are very similar to others that you may have seen before. Viscous lubrication theory is similar in some ways. We don't have inertia in viscous lubrication theory, and we omit this red term, but we have a viscous equivalent of the blue term and thickness gradients and the downslope gravity. And the Saint-Venant or shallow water equations typically are these equations, but omitting both the blue and the red terms. So omitting, because those shallow water equations are usually used for very high Reynolds number flows, it's often assumed that the viscous effects are negligible, and so we lose both of the coloured terms. So what I want to show is what kind of solutions do these equations have? Do they agree with experiments that we can do for granular flows? And the problem that I want to look at first is a problem which is sort of somewhat classical in viscous fluids, and that is what happens if we start with a point source of material and we on an inclined plane, and then we just examine how does that flow. So the viscous solution, the solution for Newtonian viscous fluids, has been known for, 30 years now. If we start with our point source here, there's no great surprise that the viscous fluid flows down the plane and it spreads out as it does so with distance to the power 3/7. But if we look at what granular flows do flowing down a mountainside, this is essentially the same problem. We have some initial source where some granular material has failed and it's flowing down the slope. But we don't necessarily see it spreading out in the way that a viscous fluid would. Instead, here are some pictures of deposits of pyroclastic flows from Mount St. Helens in the United States, in Washington State. And we can see there's all sorts of strange patterns going on here. In particular, the flow doesn't seem to be spreading out particularly. Instead, it seems to be rather channelized between these sort of lateral humps, which we call levees. And this doesn't just happen in pyroclastic flows, it's the same thing in snow avalanches. Here's a snow avalanche actually again in Washington State in Olympia National Park, where the snow avalanche has been sort of formed from a point source somewhere up here and has flown down, and we can see it's got more or less constant width. Again with these lateral levees, and it's come to a halt here. Again, a point source of the snow avalanche here, instead of spreading out uniformly over this slope, is forming different channels of constant width. And we see the same thing even on rockfalls on the moon, lead to these sort of almost constant width, sort of finger-like terminations. And so what I'd like to present first is some work by the student Chico Rocha, who looked at this in the granular case. And I'm going to start playing this video because it's quite a long one. What we're doing here is putting a point source of mass of granular material, red sand, onto a plane just up here. And what we can see is that it doesn't spread out. Instead, what it forms is two static lateral levees. It forms a steady state. And these levees act to confine the width of the flow. And so you can see here, here's a time sequence. Here's the flow first coming down. It forms these lateral levees. And I think this is quite a long video, so I might not wait for it to run out fully. But when we stop the material at the source here, we find that the material drains out and leaves a static deposit, which is this fourth picture over here, where we've got a kind of indented channel. And this is the static layer left behind on the slope in this case. And we've just seen the video has just done that, and we can see what the static deposit looks like. And key to this flow then is this interaction between the static levee, the static material, which is kind of confining the flow, and the flow itself. And we can see in this zoom in that there's lots of sort of fluctuations and interaction going on here. So there's some kind of dynamical equilibrium being set up where the flow knows that it wants the boundary between flow and levee to be at around this point. This is where the interaction between static and moving material is. And that point changes depending on the flux. Fairly self-evidently, if we put more flux down, we end up with a wider flow. Interestingly, we don't end up with a deeper flow. And so that was one of the questions we wanted to answer. Why does the flow not get deeper? Why does it get wider instead when we increase the flux? So let's have a look at how we can model that using the depth integrated equations that I showed on a previous slide. And this is in some ways a relatively simple problem because it's a steady and uniaxial flow. And so we can get rid of some of our equations. We only need to look at the downslope flow, and we have the downslope velocity u bar is a function now only of the cross slope distance y. It doesn't depend on x or t. And we can simplify our momentum equation on that basis. And we end up with three things going on. One thing is this first term, which is the gravity pulling material down the slope. We've got the blue term, which is the frictional resistance between the base and the grains, which is resisting that. And we've also got this red term, which is viscous stresses in the cross slope direction. And so the equation we have to solve is this. This equation is an ordinary differential equation because of this d squared u bar by dy squared. And we also have a constraint that we know how much material we're putting into this flow. We're putting in some flux qv, and this is the integral from minus w over 2 to w over 2, that is from one side of the flowing part to the other side of the flowing part of h times u bar, and we specify that. And so, as I say, we have a second order boundary value problem. We have two unknowns. We don't know what thickness the flow is ahead of time, and we don't know what width the flow is ahead of time. But we actually have enough boundary conditions to solve this problem because we have the specified flux that we're putting in, which turns out to be like an integral constraint, as I showed, over our velocity. And then we have three independent boundary conditions. And that is that the velocity and the shear stress at the boundary between the channel and the levee is both 0. And what this means is we're really saying that the flow, when the flow hits the levee, so when the static and flowing material meet, we have to be consistent and say that the stress that the fluid is imposing on that static material is no greater than the stress that that material can withstand before it yields. And in the depth integrated sense, this turns out to be du bar by dy is equal to 0. And so with these boundary conditions, we can solve this boundary value problem, and we end up finding the velocity u bar in millimeters a second against y, this cross slope direction. And so for different fluxes in grams per second, we see different widths of the flow, But always we see this structure where, at least for enough flux, we see a relatively constant velocity across the center of the channel, and then two boundary layers which connect to the static levees on either side. And what we have here is kind of an interesting balance between these terms in the equations. We get these shear bands, these boundary layers at the edge of the flow, because there are two different regions in the flow. When we're very near the levee wall, so very near the edge of the flow, we're in a situation where the flow kind of wants to stop. The friction on the base of the flow is telling the flow to stop, but these lateral stresses across the width of the channel are still dragging that material forward slightly. And this is the case where we've got d squared u bar by dy squared is greater than naught. But near the channel center, the material, in a sense, wants to accelerate to a faster flow rate, but is being dragged backwards by these lateral shear stresses that have to connect it back to the wall. And so in this problem, the lateral shear stresses, even though they're not usually a constituent of these kind of depth integrated models, are really crucial for determining the flow structure, because they tell us how this connection between the flow in the center of the channel and the flow in the levee, and the static levee, I should say, actually happens. If we compare the theory that we've just done with experiments, and there have been a couple of groups that have done experiments of this without the theory to go with it, we can see that we predict in blue, our blue line here, reasonably good predictions of the width of the channel as a function of the mass flux in grams per second. Again, we predict that the thickness of the flow is almost constant, and that's exactly what we see in experiments 2. And also the downstream velocity is nearly constant. Now, downstream velocity, we can't actually measure the depth integrated velocity directly, but we can measure the surface velocity, and we see a, relatively speaking, roughly constant velocity there. So we're in reasonably good, at least qualitative agreement here with the kinds of behavior that we see in the experiments. We can look also at comparisons with different materials. The previous comparisons were with sand. Here we get similar things. The comparison is maybe not quite so good on width when we're looking at spherical glass beads instead of angular sand particles. But again, we're seeing constant thickness and a width that scales with the flux that's being put in. So I want to explain why these different bits of physics are important. And to do that, I want to just illustrate what happens if we don't include this lateral viscous stress term in the equations. If we assume that this viscosity nu is 0, which is what is done in most granular, depth-integrated granular flow modeling, what's interesting about this problem, because of the fact that it's uniaxial, this is a singular perturbation to this problem. The nu here multiplies the highest, in fact, the only derivative in this equation. And so the difference between assuming that this quantity is 0 and this quantity being small but finite is fundamentally is a fundamental difference. And so if we were to set this to 0, what we actually just get is an algebraic equation on the right-hand side, and our equation is degenerate. It just tells us that the basal friction must equal the tangent of the slope angle everywhere. And if we look at our graph of our basal friction against the Froude number, this non-dimensional flow speed, what we can see is that for different thicknesses, yes, there are, in fact, 3 solutions potentially for static, intermediate, and what we call dynamic solutions to this. So there are multiple possible solutions, but we can't tell which of those solutions is the right one. And we can't tell in particular what the thickness of the flow is. So we end up effectively missing an equation. All we can tell is that the volume flux must be equal to the width times the height times the velocity, which we know is a function of the height. But we're still missing one equation here to determine the thickness. And so if we take this small parameter and set it to 0, we cannot determine the solution to the equations. Whereas if we did what I showed, I'll just zoom back to the previous slides, if we include that parameter in the equations, even though it could be arbitrarily small, this allows us to describe this interaction between the static and moving flow regions. So this shows us then that using these granular flow equations, we can predict things like what the spread, or indeed the lack of spread, of granular material is when we start it from a point source. But what this also predicts, and apologies, I'm going to jump back a little bit just so that I can show this in the graph. What we also see is that our theoretical prediction is that thickness of the flow is roughly constant along this blue line, but you can see that I've drawn well, Chico more accurately has drawn a red dotted line at lower mass fluxes, and here our solutions sort of cease to exist beneath some mass flux. So this suggests that if we turn the mass flux down in experiments to some way below this threshold that we've calculated theoretically, we may see something different, because our theory predicts that there is no steady uniform flow for this low mass flux. So let's see what actually happens. So this is a very small amount of material, very low flux of material being put onto an inclined plane. And you can see here that this flow is by no means steady or uniform. It's not forming that parallel leveed flow that we saw before. Instead, what we're looking at is a flow which is fully time dependent, and we can model that if we solve the full time dependent partial differential equations that I showed you before. So this is that set of partial differential equations for the thickness and depth average velocity of the flow. And we get similar behavior in the experiments and in the simulations. What we're seeing is this sort of periodic pulsing avalanche, where each avalanche that comes down is increasing the length of the deposit from the avalanche. And the avalanche is actually not flowing over, it's not flowing very effectively over just the plane, but what it can do is erode granular material from in front of the flow and deposit it behind. And so we get these sort of pulses and waves traveling down the flow. The color map here is showing the downslope velocity. So blue material here is material which is completely stationary, which we can see here in parts of the flow, the experimental flow. And we have these pulses of material flowing downstream, just as we have in the experiment. And so this is a kind of pretty exciting, exciting and different flow. It's not forming this simple channeled flow. And so we thought we'd look at that in a bit more detail. So this is just showing a cross-section through the middle of that flow, just looking at the height in blue and the velocity in red, and just showing this sort of pulsing behavior that we can see. And if we look at the thickness at a given point as a function of time, we can see these sort of pulses periodically, and that's exactly the same as what we and others have seen in experiments for this flow. And indeed, it's exactly the same as what you see in nature. So this is a very old video, so apologies for the quality, but what we can see here is the static deposit of a debris flow, and there's a wave that's pushing that deposit towards us. But this is being pushed towards us, and so the very front of the flow has just gone below the bottom of the camera. But as you can see, it's just sort of coming to a stop now. Everything's coming to rest. And we can see that the flow's come to rest, but upstream, there's another wave coming downstream down the channel towards us. It's remobilizing this previous deposit and pushing the front of the flow another 20, 50 meters downstream. And so this is exactly the same behavior that we see in the lab and in our numerical simulations, but we're seeing it now here in a real debris flow. This video was made in, this video was published in 1980, so this is a flow from many, many years ago. And just a little bit later on in the flow, once that flow front has passed, they kept filming, and we can see here more of these waves coming down, just a periodic sequence of these sort of soliton-like waves separated by static material. So the material redeposits and is static for a while before another wave comes and re-erodes it and travels downstream again. And a slightly more recent video, this is from a town called Fully in Switzerland, where there was an accidental release of water from a lake high up in the mountains. And this precipitated a debris flow where we see very similar things. We see these surge waves rolling down a layer of existing deposited material. And once we zoom in here, you can see that it's destroying some vineyards. Fortunately, no one was hurt in this flow, but a number of hectares of vineyards were lost. But you can see we've got exactly the same structure. There are these discrete pulses of waves separated by regions where the material has fully deposited and has stopped. And an interesting thing here is that these waves seem much better able to propagate over a deposit of existing material than they do over a completely empty plane. So we did some experiments to look at this. And what we did was we laid down some layer of thickness H0 of red sand on an inclined plane. And then we released some yellow sand on top of that and saw what that did. So I'm just going to show a video here to show what happens. There's a release of some yellow sand, and we can see that it travels down slope, but there's obviously a mixing of the red sand and the yellow sand. Here's another smaller flow. We can see that, in fact, the yellow sand, let's see if I can pause this, not easily. I'll show you some pictures shortly. The yellow sand gets deposited quite close to the where it was dropped, but the avalanche continues propagating down, but is now formed of red sand that has been eroded. So let's just look at a time sequence of one of these things. If we drop a volume of yellow sand just on the inclined plane, which here is it's green in color, without an erodible layer beneath it, it stops very rapidly. But if we drop that same volume of yellow sand at the same inclination angle of the plane, we end up, but this time we have some layer of red sand. We see that the avalanche continues propagating, actually indefinitely in this case, but the yellow sand is still being deposited out. You can see that by 3.4 seconds down here, there's very little yellow sand left in the avalanche, but instead there's a big chunk of red sand at the front here, and the avalanche is increasingly being composed of sand not that was the material that was originally released, but material that was eroded from further down the slope. And what we see, depending on the thickness of both the inclined plane, the thickness of the layer on the inclined plane, the thickness of this red deposited layer, and the inclination angle of the plane, there are 4 different modes that we see. One of which is that the avalanche deposits more material than it erodes, and then we get this decaying avalanche which stops at some length. We get avalanches which propagate indefinitely, keeping a steady width. But as you can see again, the yellow sand that we've released has largely been deposited, and it propagates indefinitely then as a purely red avalanche. At steeper slope angles, we can get avalanches which grow, so they build up more and more material as they go, getting bigger and bigger. And then even steeper still, we sometimes see these shedding avalanches where the avalanche drops smaller drops smaller avalanches behind it, and sometimes these can split apart and keep flowing themselves. And so there's various different sort of flow phenomena we can see. So how can we model these types of things? Well, we can do that using exactly the same equations that I showed previously. We've got our mass and momentum equations. These are just the same. I've removed the coloring, but they're just the same equations for the mass and momentum of our grains. But what we're also doing is we're tracking the position of yellow particles. What we do is we consider all of our yellow particles to start at some position R, and we just advect them around by saying that the rate of change of their position is equal to the velocity in our flow at their location. Now, this requires us to reconstruct the 3-dimensional velocity field from our depth averaged velocity field. But that can be done by assuming a velocity profile like the profiles that we calculated at the very start, where we knew u as a function of z. And then we can use a divergence-free condition which calculates the vertical motion of the particles as well. So this is a bit of an approximation, but it does allow us to track where the yellow particles are going to be within these avalanches that are mixing red and yellow particles. And so what we find is that by solving these equations, these again are numerical solutions of that system of partial differential equations, we can recreate exactly the same kind of behavior that we see in the lab. So what I'm showing here is a kind of 3D visualization showing the thickness of the flow, and I'm brightening the material that is actually flowing. And so this lighter region at the front is the material that is flowing. Everything behind has been deposited already. And we see much the same kind of behavior. We see yellow particles here being deposited mostly near the source, and then the flow continuing a little while on red particles. And at this slope angle, we can see that the flow has come to rest. This steeper slope angle, we see that the yellow particles again deposit. Interesting. We don't see that. We see that I appear to have the wrong video there. Let's hope this one works. That one works. Okay. Apologies, I got my middle video wrongly. So this video on the right-hand side, we are looking at a flow where the slope angle is somewhat steeper than the one on the left-hand side. And as we saw in the experiment, this is a growing avalanche where those parallel levees are not parallel, they're getting further and further apart. In this case, they get closer and closer together in the first case, and in the middle case, for which I couldn't get the video to run, they are parallel because the flow is traveling downslope perfectly. So it's forming this kind of a steady traveling wave where these levees remain at a constant distance from each other all the way downslope. And so we can clearly see here many of the sort of qualitative phenomena that we are seeing in the laboratory experiments. And that's all coming from those partial differential equations where we're putting in the correct granular friction law, which is describing both static and moving material, alongside the mass and momentum equations, which govern, just come from kind of mechanics. And so just to look at that comparison between experimental flows and theoretical flows a little bit more closely, here I've got a phase diagram. V is the volume on the vertical axis here. V is the volume of material that I'm releasing onto the incline, and zeta is the slope angle. And we can see here that these four regimes, decaying, steady, growing, and shedding, the experimental flows are open circles, the theoretical predictions are closed circles. And we can see that we've got this phase diagram, which is more or less in agreement between theory and experiment, which is predicting this phenomena that at low slope angles, we see these decaying avalanches. Then as we increase the angle, we get towards steady state avalanches, growing avalanches, and avalanches which shed other avalanches behind them. And we can see also that we can predict other flow phenomena. So what we're looking at here is the downslope position of the front, xf in meters. So this is how far the front of that avalanche is propagated as a function of time for some different avalanches. The colors here are not necessarily exactly in correspondence with these, but red is a decaying avalanche here. So in the experiment, we see that the avalanche propagates, and so apologies. In the experiment, we see the red dots, so the red circles, and so this avalanche is propagating. In the numerics, we see that it stops rather more quickly. The experimental flow does stop, but after 5 seconds. The agreement there is not so good, but for these other cases, we're getting good prediction of the downslope position of the front as a function of time. So we're roughly capturing the speed at which this front propagates downslope. And we can also predict the width of the flow as a function of the downstream distance. And so red here is one of these decaying flows. You can see here that again, our numerical prediction, the solid line, decays rather more rapidly than the experiments in the circles, but nonetheless, both of those are those decaying flows which stop after a while. And then we've got various different combinations of more or less steady state flows, say in blue here, or growing flows. This one in green is widening as it progresses. And although we're not capturing the width exactly, you can see that we have qualitative agreement here between the green line and the green circles. So the gradients are being matched quite well in those cases, even if there's some offset in the width, which we're not exactly capturing. And so these kinds of models, hopefully I've shown that we can capture quite a wide variety of quite complex granular phenomena, particularly when we've got both static and moving materials of grains interacting with one another in the same flow. One thing we can do, because we're tracking these yellow particles, is we can look at where those particles end up in the flow. So I'm just very briefly going to play a couple of videos showing this is now a cross-section through the flow of our simulation, and we can see this prediction that the yellow particles in some cases are all deposited very close to the place where the flow is released, and then we get the remainder of the deposit here is purely red particles. In other cases, we actually see that some yellow particles get trapped right at the front of the flow. You can see that there's a kind of cluster of yellow particles here. And this is something that I haven't got time to talk about today, but we've looked into in quite a bit more detail. And we can kind of look and see how yellow particles end up being recirculated through the flow and mixed in to the deposit by these avalanches that propagate through it. And I just want to finish by showing that there's a lot of other things that we can remodel, and I'll show you this incredibly busy video showing a couple of the experiments that I've shown already today, but a number of other things that we've looked at in the lab in Manchester, in particular where we've got multiple different sizes and multiple different colors of grains and how those mix and segregate through one another. And all these types of flows can be modeled quite effectively using this depth integrated framework that I've shown. So with that, I'd just like to conclude by saying, as I've shown, many natural granular avalanches are involving these complex interactions between static and flowing material. And we really need to understand that by looking in detail at what the friction law does as we transition between these states in order to model that. But if we do that, these depth integrated models that I've shown are effective at capturing, at least qualitatively, a very wide variety of these complex phenomena that we see in nature. So thank you very much.
Thank you very much, Chris. It was a wonderful talk. Thank you so much for this, for showing us this beautiful merge of equations, numerical solutions, and experiments carried out by mathematicians. That's something that people are not often used to see, right? So we have some people saying that was a nice talk on the YouTube chat. We do have questions. So please post your questions on the YouTube chat and I will read them to Chris and then we can establish some sort of discussion here. So I will start with a question by Albans Atman. So Albans is asking, how does the width of the fingers depend on the granulometry? More specifically, does the width increase if larger grains are present in the avalanche flow?
That's a great question. So generally speaking, if we have large grains, the width probably tends to decrease. I'm going to play this video again because this video in the top right shows a flow where we have got large black grains and small white grains. And what we see is that the large grains get pushed into the Levee walls. In fact, this is almost where we started in this problem. We started looking at why the large grains get pushed into the sides. And because large grains in natural flows are effectively more frictional because the poor water can dissipate out of those more readily, we think that will end up confining the flow more than expanding it if large grains are present. But fully understanding the couplings between the morphology, the rheology, and the granulometry of these flows is still an ongoing topic of research.
All right. So I will carry on Alban's question. So is it possible that once you've established a Levee on a steady state flow, can it be eroded, Chris?
Yes, absolutely. So I rushed over this, but if we look at these three flows
Can we have the slides back again,
apologies.
please?
If we look at these three flows here, 25 grams a second is the original flux. This is actually the same flow where we reduced the flux to 7.7, and we can see that wide levees are left because it's still the width left over from the 25. But if we
Right.
increase it to 27, that's pushed the levees outwards a little bit. So if we increase the flux, we start eroding the existing levees and building new ones further out.
I see. So in a steady state regime, what you see is that there is a similar amount of deposited material and eroded material. So there's a non-zero erosion.
Absolutely. So the fluctuations we can see at the top here, as you can see, it's eroding and depositing continuously, but those two processes are in balance.
Right.
And if you increase the flux, the erosion starts to win and it starts to erode outwards. If you decrease the flux, the erosion starts to lose. And that's actually because as you change the flux, the thickness of the flow varies very slightly, and which of erosion and deposition wins and is more powerful is very, very sensitive to the thickness.
I see.
So that's what controls it.
Yeah, I see. That's very interesting. So while we wait for potentially, okay, we have a question by Enzo. Enzo is asking, an amazing talk. Which software did you use to create the plots?
A mixture of things. Most of this, I would say, is MATLAB. MATLAB scripts and lots of head scratching to try and get MATLAB to do what we want it to do rather than what MATLAB wants to do. And staying on the same version of MATLAB, because when you change version, it changes your plots.
Yes.
But yeah, lots of PhD student time, including Chico's, went into making these great plots. So I thank them greatly for that.
Very good, very good. So I'll take on that question by Enzo. And I saw, Chris, on your two-dimensional plots of the solutions of the unsteady avalanches. I think you showed us the unsteady avalanches, and you had a cross section, and you showed us just the height.
Yes.
Yeah, that one I think. So we can clearly see waves propagating up and down, and they do have this peak shapes. So how smooth are these peaks, and how have you dealt with backwards propagating waves or retroceding waves with negative velocities in terms of numerical schemes?
So the flows that we're looking at here, if we did not have the higher order stress terms, would have shocks in them. The hyperbolic equations, they would have shocks. Those shocks are resolved because we are using a shock capturing numerical method. We tend to use the Kurganov and Tadmor non-oscillatory central type numerical methods, which resolve the shocks even if we don't have viscosity in, because the physical shocks that we get in the system are from mass and momentum conservation, and those are the ones that we end up with in for that particular set of hyperbolic fluxes.
Right.
And those can resolve both the kind of eroding fronts that we're getting going downslope, and they can also resolve the bores that, as you noted, propagate back upslope. Now, we are actually adding this viscous term, which smooths those out slightly, but we still get those kind of the correct shock propagation behavior, largely thanks to using these non-oscillatory schemes, which are designed to be shock capturing.
Excellent. Yeah, very good. Thank you, Chris. So let me see if we have more questions here. So apparently not. I will ask another question, Chris, if we still have a few minutes. So you mentioned on, I think it was on the final slides where you presented your shallow water theory. I think there was on the dissipation term, there was a mu b term there.
Yes.
And you pointed to that term saying that we have to capture the right friction, the correct friction term. So whenever we see mu on these equations, we often immediately think about mu of I rheology.
Yes.
Is that mu of I rheology, or is that the specific law that you designed for the base friction?
This is the specific law that we designed for the base friction.
Right.
So what, if I just scroll back to this plot, this description of the relationship between fluid number and thickness is what is behind the both black regions and the red region, all three regions are what comes into our mu b, our base law friction rheology. the mu of rheology only describes this upper black branch. It doesn't describe the red or the black or the static material. If we had the mu of rheology, what that predicts is, if we go all the way back to slide 1, that predicts that line continues all the way down, straight line back down to 0.
Mm-hmm. And that's why we often see granular simulations using the mu of rheology that are a bit too fluidy, right? Because
I think
they don't
so.
capture the solid behavior.
We don't capture that. We don't capture the hysteresis. We don't capture static material in this way. The reason why is because this H dot behavior comes from non-locality, and the whole assumption behind mu of I is that the dimensional analysis that leads to it comes entirely from it being functions of local flow properties, and we know that's not true. And that's one reason why we have to use depth integrated modeling, because nobody yet has a full constitutive rheology which will reproduce this full behavior for granular flows down an incline. Obviously, some people have tried to put in non-locality, but it doesn't capture quite everything that we need in terms of H start and H stop and the right behavior here to get what we need to model these flows. The flows that I was looking at actually turn out, because they've got this strong interaction between static and flowing states, turn out to be pretty sensitive to what exactly we do. And so, in a sense, they're a good test bed for these kinds of rheologies, because they're a way of looking at flows that really care about what happens at very slow states, slow shear rates, rather than more rapid flows where you're probably okay with just this upper mu of rheology line. Who's okay? I can no longer see or hear Yuri, but let's just wait a little and we'll see if he can reconnect. Okay, so it looks like Yuri is having some technical difficulty with connection. I'll just leave it 1 minute and see if he can reconnect. Okay, I'll give it just 1 minute, and then I will look to close this session myself. Let's just see if you can come back then, but if not, I will leave it there. Okay. Okay, so it looks like Yuri has been unable to connect. So in which case, I'll just say thank you all so much for listening to my talk. As I say, enormous pleasure to do this. And yeah, I look forward to seeing many of you on Zoom on the Granular Day that's going to continue later on today. So thanks very much.